everyone. All right, are you ready to get started in a new chapter? Chapter 7 is on systems of equations. This is something you should have seen prior to this course. You probably even clear back into Algebra 1, Algebra 2 would be where you would have seen solving systems of equations. To start with, what is a solution to a system? Well, a system is basically when you have multiple equations, and we call that a system. And it might be two equations, but it can be more than two. For right now, we're going to stick with two equations. And the solution to it is the ordered pair that satisfies all of the equations in the system. So it's an xy coordinate that would work in both equations. Graphically, what it means is if you were to graph the two equations, that it's where they touch, where they intersect. And so from what you've previously done, you'd have some methods to solve a system. One of those methods would have been graphing, just to look at a graph and find where they intersect. And and that works great to kind of visualize what's going on. Sometimes it's tough because they don't intersect in nice places, and so we have some more algebraic methods. We sometimes use substitution. And other times we'll use elimination. It kind of depends on what the equations look like on which method you would want to use. Now, in your previous experience in solving systems, everything was probably linear. And so just to kind of refresh your memory, if you have something that's linear, it's either going to look like something that's in slope-intercept form. Well, here, let's just do this. Let's just give you an actual equation. So it's going to look something like maybe y equals 2x plus 3. Or maybe it'll be something that's in standard form, might be 2x plus y equals 7. Those would be linear equations like you're used to. But now, when we're solving systems, we're going to be throwing some other types of equations in there. You might get some kind of a quadratic. Now remember, a quadratic is going to have a y with some sort of an x squared somewhere in there. Might look like that. You might have a cubic where it might look the same way, only it's cubed. You could have a circle, and we'll do some of those. Remember that a circle has this format. It's something like x plus 3 squared plus y minus 2 squared equals 16, or something like that. So the x will be squared and so will the y. Both of them are squared. And then this would tell you how much to move left or right. This would tell you how much to move up or down. Since they're inside parentheses, you'd always do the opposite. And then this is the radius squared. So in this example, the radius of my circle would be 4. All right, so those are the different types of equations you're going to see. And it could be more than that, but let's look at what your solutions are going to look like. All right, so you could possibly end up with a no solution. Remember, what you're looking for is where the two graphs intersect. So I'm going to throw some graphs on here so you can see what the scenario would be. So if you had two lines, we'll always start with that because that's what you're familiar with. To have a no solution, your two lines would have to be parallel lines, and then they would never touch, so there's not this point of intersection or a solution. But you might also have other types of graphs. So you might have like a parabola with a circle. Okay, those two never touch, aren't going to touch even if I extend with those arrows, and so that'd be a no solution. Okay, a one solution, well, is going to be kind of a typical two lines intersecting, here's the solution. But it could also be like a parabola with a line, and that line might just come over here and just be tangent. For a two solution to work, it wouldn't really work with two lines. The most you could have is just the one, but you could do something like with a parabola and a line going through there. That would be two solutions because it touches twice. You could do a circle with a parabola, something like that would have two solutions. You could really make this, as long as you start including other types of graphs, you could do 3 solutions, 4 solutions. Let's move on and let's look at infinite solutions. To have infinite solutions, what that means is that you've got one line right here, and then when you graph your second line, it ends up right on top of it. which means that they would touch everywhere, so there would be an infinite number of places that you could call a solution. And so that could happen also then with a circle. You could have infinite solutions where one circle ends up landing on top of the other one. Okay, so that just be looking for some other things to happen other than always having just one solution. Okay, so let's start with this one. Now, of the three methods that we have to solve a system, we're going to look at substitution first. Substitution works awesome when you have a variable that is sitting by itself. Now in this case, I don't have a variable that's all by itself, but this y here is pretty close to being by itself. It would be real quick and easy to subtract 2x on both sides and end up with y equals negative 2x plus 5. Now I could write that as 5 minus 2x. I'm just in the habit of putting it in slope-intercept form. It doesn't have to. Either way is fine because I'm not really graphing here. All right, so what I've figured out then is that this right here is what y is equal to. So I'm going to take that and substitute it in for y in my other equation. So then I'm going to rewrite this as a 3x minus 2, and then instead of the y, I'm going to have negative 2x plus 5 equals 4. So you isolate a variable, and then you plug what that's equal to into the other equation. And then let's clean this up. 3x, I'm going to end up with a plus 4x minus 10 equals 4. Now what I've managed to gain here is that I only have one variable now. In those other two equations I had two variables, but by substituting in I've eliminated that y value and now I only have an x. All right, I'm going to add that 10 to the other side and then divide by 7. Works beautifully. I got x to be equal to 2. But what I'm looking for, remember, is an ordered pair. So what I have right now is the x value, and so I'm going to take this 2 that x is equal to and go plug it in. And I can plug it in into either one of the originals, but it's usually best to plug it in right here because you've already done all the work at trying to get the y by itself. So now what I end up with is a negative 2, and I'll go ahead and write this out, y equals negative 2, and then I replace the x with 2 plus 5. And probably as you do more of these, you're going to do this step here in your head where you can just plug in the 2 and say, oh, I would end up with a 1 for my y value. Okay, so then your solution should always be written as an ordered pair, x comma y. So my solution on this problem is 2 comma 1. That's the point where those two lines would intersect. And not only is that where the two lines would intersect, but this is also the ordered pair x comma y that would work in both of these equations. If I put 2 in for x right here, then I'd have 2 times 2, and that would be a 4, plus, and then for the y, I'm going to plug in the 1 that I got, and I have 4 plus 1 equals 5. Yeah, that works. Very good. Let's try it on the bottom equation. If I plug 2 in for x, I'd have 3 times 2, which is 6, minus, plug 1 in for the y, is 2. Hey, yeah, that does equal 4. So that's the other thing, that makes both of those equations true. Okay, so let's try another one, a little bit trickier. So when you look at the top equation, this is not a linear equation anymore. I have a y, and then I have this x squared going on. So whenever your y is linear and your x is squared, that's a quadratic, that's a parabola. All right, so I have a parabola, and then the second equation is a linear equation. So if you think of a parabola and a line, I have some options here on what might happen. This might never intersect. It might intersect just once right there at that spot. Oops, missed it at this spot. Or maybe it could even intersect twice. So I have some options on what I'm going to end up with for an answer. Let's jump in and do some substitution. Now when you're substituting, you always want to pick the easiest variable to get by itself. That'll make your life easier. So when I look at this, probably what I'm going to do is work on getting this y right here by itself, and then I'll plug this, whatever I end up with, in for y right there. And then I'll have everything in this big equation, and then I can start combining some like terms. Okay, so first step, let's get that y by itself. So I'm going to subtract the 2x, So I'll have a negative y equals a negative 2x minus 1. That's a 1. That font is kind of bad. This is a 7. This has just a little mark on it, so that's a 1. Okay, and then the next thing I need to do is multiply through by a negative 1 to get my y value positive. Okay, so once you've isolated the variable, you take that and you plug it in for y in the other equation, right there. Okay, now there's nothing magic about always choosing y to solve for. You really look at your equations and pick the one that's the easiest. Last time we solved for y, this time again, just because that was the easy one to do. Okay, so now what I have on this top equation is an x squared plus 4x minus, be really careful with this, I find a lot of errors with this part right here. You're going to subtract that entire quantity. So that minus sign is going to affect both of those terms. So we end up with an x squared plus 4x minus 2x minus 1 equals 7. All right, so now since this is a quadratic, I'm going to end up trying to factor this. So let's bring everything to the same side, combine our like terms. So I'm going to have an x squared, 4x minus 2x is 2x. Let's subtract the 7 over to this side. And we end up with this nice little quadratic that we need to factor. Factors of 8 that have a difference of 2, that have to be a 4 and a 2. We'd want a plus 4 minus 2. All right, so x is going to be equal to 2 and negative 4. All right, so I actually have two options for my x value. So what that means is I'm going to plug them in to the y to get their matching y values. So right here I'm going to take this 2 and I'm going to plug it in. This is the easiest spot to plug it in right there. So when I plug in 2, I'll have 2 times 2 plus 1. That would end up equaling 5. So one of my solutions is an x value of 2 with a y value of 5. Then you do it again, only this time we're going to take the negative 4 and plug it in. So take negative 4 and plug it in for x. So 2 times negative 4 is negative 8, plus 1 is negative 7. So then I'd have a negative 4 for an x value and a negative 7 for a y value. So this is one of those ones that has two solutions, so it must have been something similar to that. Not that that has to be a horizontal line, but just anywhere it touched twice there. All right, there's my solution. Okay, let's look at this one. Looks like another linear situation and another quadratic situation. So on this one, what I'd like to do is have you try it by yourself. When I look at these, I'm probably going to, let's just so that we get started on the same path, probably looking at as far as which variable is easiest to get by itself, I would probably go for this y right here. It's already a positive versus going for this x because I'm going to have to deal with that negative there. And I kind of like to plug everything into the quadratic. And either way, you could also get this y by itself. That would work as well. But just for consistency today, let's go ahead and have everybody get this y by itself and go substitute. What I'd like you to do is pause the video, go try this one on your own. All right, let's check and see how you did. You should have ended up with an x plus 4 to substitute in. When you did that, you'd write it all out, combine your like terms right here, and then it'd be really, really tempting to factor that to x plus 1, x plus 1. But if you did that, you'd have a middle term of 2x, and I'm only supposed to have a 1x. So this problem does not factor. Not everything will factor for us anymore, so now we have to go quadratic formula. And so when I run this equation through quadratic formula, I end up at this stage right here. What about that should make us nervous? Should be this negative right here. You can't take the square root of a negative without ending up with an imaginary solution. All right, imaginary solutions are not going to be points of intersection. So if you end up doing something like this, where you have to run it through quadratic formula and you get an imaginary answer, okay, since it's imaginary, That's going to be one of those scenarios that is a no solution. So meaning that my line and my parabola that I had there are never going to intersect. And there's no ordered pair that I could make work in this equation and also make it work in this equation. It's not out there. So no solution on that one. All right, so we've done some substitution. Let's look at a graphing situation where we want to graph this. So what I've given us here is a linear equation. So that's the first one that we have, linear. And then I threw a cubic in there as a little refresher from way back in chapter 1. Okay, so let's start with the linear model. Let's put that into slope-intercept form. So I'm going to subtract the 3x. So y equals a negative 3x and a positive 2. Okay, so to graph a line, I've got to look at my y-intercept. The y-intercept is this b value on the mx plus b. So it's going to cross at 2. All right, and then I'm going to count my slope. Think of that as a negative 3 over 1. So I would go down 3, right 1, and put a point. And you kind of want to do this, since you're going to be looking at where they intersect, you're going to want to do this for as much as you can on your graph. And so I'm even going to go up 3 and left 1. Up 3 and left 1. Get as many of those as you can in there because you really need this to be an accurate graph so that you get the points of intersection accurate. All right, so there's my line. Now let's look at this cubic. All right, first thing I'm going to do is get the y by itself. So I'm going to end up with a y equals, subtract the x cubed, and add the 2. Now, you have to kind of go back on this one and think back to your parent graph, y equals x cubed. On a y equals x cubed, when you plug in 0 for x, you get 0 for y. If you plug 1 in for x, you get a 1 for y. 2 would get me an 8, and 3 I'm going to be way off of my graph at 27, so that's not going to work. But I might throw in a negative number. What if it's a negative 1? Well, negative 1 cubed is negative 1. A negative 2 cubed would get me a negative 8. Okay, so that there is the that's the table for the parent graph. Now what you have to do is look at what have we learned about the shifting and the translation and all that with this equation. So this negative does what to my equation? Hopefully you said it's going to reflect it over the x-axis. It's going to make it look upside down. All right, what does this plus 2 do? Since it's not in parentheses, that's going to move it up and down, and since it's a plus, it's going to go up 2. So what I'm going to do is I'm going to plot this y equals x cubed, and then what I'm going to do is shift all of those points. I'm going to reflect them over the x-axis, and then I'm going to move them up 2. So here we go. Let's go ahead and plot those points. 0, 0, oops, need the pen. 0, 0, 1, 1, 2, 8. Okay, now remember that's that kind of little snaky little wave thing that in there. Now I'm not going to mess with graphing that because that's not really my final graph. I'm going to change colors here and I'm going to go to my black pen and I'm going to reflect all of those points and then go up 2. So let's start with this point here. To reflect it means it has to come clear up here to basically to that blue spot right there is where it would end up. It reflects over the x-axis, but then I have to move it up 2. So then my point ends up right here. Okay, that's not a point of intersection because it didn't hit the line. But I'm going to do this with every single point. So this one right here would reflect to this spot, and then I got to go up 2. On my origin, that point doesn't really reflect. There's nowhere for it to go. It just stays there, but then I move it up 2. Oh, hey, look at that. That big glob, my first point that I put in there, that's going to end up a point of intersection because it just touched my line. All right, the next point is this one. It's going to reflect downward, but then I have to move it up 2. So it's going to land right where it started. And then the last point, here is going to reflect downwards, so it's going to land right here, and then up 2. All right, so there is my graph. Let's go ahead and graph this. And then it kind of snakes in there and then comes back down. All right, now, when you look at this, there's actually several sections. I've got this obvious one right here, but this line comes down and right here-ish, and it looks like it's that point right there, but it's not, because on the blue line, I'm over 2 and down 4, but on the black, when I'm over 2, I'm actually down 6, so that's a little bit deceiving looking. So it's probably up here somewhere a little bit higher, where that's touching, not at that spot. And same problem here, this didn't hit one of the points on my blue line. All right, so graphing is a nice visual. It's a good way to see what's going on, but it's not always ideal because I can't always find the exact point of intersection. So on this particular example, I'm going to show you how we can check our answer with substitution. We've already done a lot of the work on it. I've got the y by itself. It's a negative 3x plus 2, and I'm going to substitute it right here. All right, I didn't leave myself a whole lot of room, so let me kind of... All right, so here I go. When I substitute that, I'm going to have to go down here. X cubed minus 2 plus, and instead of y, I'm going to have a negative 3x plus 2 equals 0. All right, so, oh, look what's going to happen. My minus 2 and my plus 2 will cancel out, and I have x cubed minus 3x equals 0. All right, so in this particular example, I'm going to try to factor. I'm going to pull out an x first of all, and then I'm going to have an x squared minus 3 equals 0. All right, in a perfect world, this would have ended up a difference of squares that I could then refactor. But 3 is not a perfect square, so that's not going to work out for me. So when I set the x equal to 0, okay, that's one of my possibilities. And then my other solution is going to come from setting x squared minus 3 equal to 0. So x squared is equal to 3, square root both sides, and you end up with x equal a plus or minus root 3. All right, that is not a pretty answer, but root 3 is about 1.7. So let's check these on my graph. So the first one, when x was 0, if I wanted to check my other, what's the y value that goes with it, then it's going to go right here. So negative 3 times 0 is 0, plus 2 is 2. So one of my solutions would be an x equals 0 when my y value is 2, which makes sense because that's this point right here that I already I had found by graphing. So that matches, so that makes me feel good. Okay. Now the next thing I'm going to have to do is plug in a root 3. Now that's not going to plug in nicely. You can do it. You're going to end up taking this root 3 times a negative 3 and type it in your calculator and then add 2. And then you take a negative root 3 and plug it in and multiply it and then add 2. And ideally what you end up with is something that would match up with what we have on this. Now remember, it's over root 3, so over 1.7-ish down 6-ish, or, well, no, I'm sorry, down 4-ish or something like that. Okay, so ideally it would be something right there, and then I'd also go left root 3, because I have a negative root 3, which is 1.7, and then whatever I get back should be somewhere about right there-ish. All right, so not a great way to solve graphically. So if I'm going to do it algebraically, then let's go ahead and do that. I'm going to plug in, so I'll have a root 3, and I'll plug that in and see what I get, and then I'll have a negative root 3. So in my calculator, here I go, square root of 3, and I'm going to take that times my negative 3, and then I'm going to add 2. All right, so when I plugged that in my calculator, these were the values that I got for that, which seemed reasonable for my graph. All right. One thing to note is I'm going to be nicer on your assignment. I wanted to kind of show you kind of a harder, complex, think through all of that's going on and what you might have to do, but I'll be nicer on your graphing equations on your assignment. They should actually cross at a nice spot on both graphs, so you shouldn't have to do it both methods. On your assignment, the very first problems you do, though, they ask you to use substitution, and then they give you the graph, and they want you to confirm it. You just need to look at their graph and make sure that your answers make sense. If your answers don't look like where they intersected on their graph, then you need to check your answers. Okay, so let's try an application problem here. It says you plan to rent a 14-foot truck for a 2-day local move. At U-Haul It, you can rent a truck for $50 per day, plus pay 25 cents per mile. At Moving Up, you get a truck for $29.95 a day, and then you have to pay 49 cents per mile. Okay, so in one scenario, it is expensive up front, but it's cheaper per mile. So that would be a good plan if you didn't have very far to go. This one is cheaper up front. Okay, let me backtrack. I'm sorry. Let me say that again. This would be $50, and then it's cheap per mile. So this would be good if you had a long ways to go because it's cheaper for the mileage. So if you're going across country or something like that, you'd want a cheap mileage fee. At Moving Up, it's cheaper up front, but you're going to pay per mile a lot more. So if you didn't have very far to go, you wouldn't care so much about that. So when we say which is the better deal, well, it really depends. We don't know which one is better because I'm not sure how far we're going. If I had to just guess, it did say it was a local move, meaning I'm probably not going very far. So my guess would probably be to go with this one. But here's the thing is, what's the cutoff? At what point is not very far? And so what we're going to do is we're going to kind of find the spot where those two companies end up costing the same amount of money. And that's basically going to be a couple lines, and I'll look at where they intersect, and that will be the solution to the system. And then I'll kind of write a nice sentence to interpret that. Okay, so let's look at what we've got for equations. One of our equations, for the U-Haul It equation, and I'm just writing an equation on what it's going to cost me. So my first equation, as far as the U-Haul It, will cost me, so I'll have y equals, y is going to be my cost. It's going to cost me $50 per day. And notice that it's a 2-day move. So actually it's not $50, it's actually going to be $100 because I'm doing it for 2 days. Plus, I also am going to have to pay 25 cents for every mile, and I'll let X stand for miles. Okay, see if you can write the equation then for Moving Up. All right, these should be your two equations. The second one, don't forget that it was a 2-day move, so you had to double the fee, and then it's 49 cents a mile. Now, just to get an idea of what's going on, these are really almost in slope-intercept form. If I switched this around, 0.25x, 0.25 is my m, my b is 100. So if I were to graph that one, I'd be up here at 100, and it's a, I don't know, I didn't leave myself much room. Let's make this be 100 instead. Okay, and then my slope is positive, so it's going upward. All right, if I were to graph that second equation, the y-intercept on that one is a little bit lower. It's closer to 60, so it's about right there. It still has a positive slope, but notice that the slope is bigger than on the original equation, which is going to make my line be steeper. And so it's going to look something like that. And so what I'm trying to find is this point right here where the two companies cost the same. That's the solution to the system. So what you're going to do is substitution. So since this is what y is equal to, I'm going to plug it into y in my other equation. And basically what I end up doing is setting those two things equal to each other then. Those two expenses. Okay, why don't you take a minute and go ahead and solve for x. Okay, I went a little bit farther. Once I solved for x, I got 167.1. I plugged it back into the original equation and got my y value to be 141.8. All right, now we could write this as an ordered pair, but on any type of an application problem, I want to know what's it mean? What's that ordered pair mean in this problem? So if you think about what our x value was, our x was how many miles. So across here are the miles. The y was how much it was going to cost me. So this is my cost up the y-axis. And so since what I found is the spot where they're the same, I should come back and write some nice little sentence about the two companies will both cost, and the y is the cost. So, oh, I should have kept 2 decimal places. What did I have? I had 7.78 is what I had for a decimal there. So that's money, so we go 2 decimal places on that. When I travel 167.1 miles. Okay, so now let's go back and really think a little bit deeper. So which one should I use? Well, I know that my cutoff is 167.1 miles. And so anytime that my mileage is less than that, that's going to be this part here, I should be using that second equation, this one here, because the mileage is expensive, but I'm not going very far. So let's come back and write one more little statement about if I travel or move or whatever less than 167.1 miles, then I should use that second company, and that second company, remember, was called Moving Up. So then I should use Moving Up. And then obviously, if it's more than that, more than 167.1, then I'd want to use U-Haul it. All right, there you have it. A nice application one. You have several application problems on your assignment. In fact, through this whole chapter, there's quite a bit of application with systems of equations. So lucky you, we are going to do a bunch of them. All right, good luck.